Hi, I'm KSpoerl, and today I'm going to be talking about the power management system inside of a common cell phone. Now, it's important to realize that this system is made up of two key components, the rectifier circuit and the RC circuit. So in this video, I'm going to be breaking down both of these circuits to determine how both function and determine the output of our system. So the first circuit I'm going to be analyzing is the rectifier circuit. Now it's important to note that this circuit is a nonlinear system and it is a time invariant system. Now it's a nonlinear system because it fails to satisfy two key clauses of linearity, which are homogeneity and additivity. Now it fails to satisfy homogeneity because if I were to multiply this AC input by -1, I would get an inverse sinusoidal input. Now, you would expect, if it's satisfied homogeneity, that to reflect in the output. So I would get a negative output here, but that's not the case. And this is because the rectifier circuit acts as an absolute value function for the output versus the input. So in this case, the output would be the exact same. Now, it fails to satisfy additivity because if I were to add the positive sinusoidal wave right here and a negative sinusoidal wave, you would expect then the input to be 0, and you would expect that to be reflected in the output. So it would be 0. But in this case, since the rectifier again acts as an absolute value function, it would simply double the value of the output right here. So in order to better understand the circuit, we also need to have a fundamental understanding of the functionality of diodes. So a diode will let current through once it reaches a certain threshold voltage. Now, this threshold voltage determines at what point this diode stops acting as an open circuit and starts acting as a short circuit. Now, this threshold voltage can be seen visually here in this technical schematic of the diode showing a PN junction. Now, in the middle of this PN junction, there is something called the depletion region. Now, this region's distance can determine the threshold voltage of the system, and we can know this by using equations from electromagnetics. So we know that the voltage is equal to the integral of the electric field, and in this case we know that the electric field is equal to the integral of the charge density of this depletion region over the constant associated with the material in the depletion region. So both the charge density and the epsilon constant of the material are both constants in the system. So what we really care about is the limits over what we're integrating over. So in this case, we have, say, a negative d here and a positive d here. So if we integrated along that distance, we would receive the electric field. And then if we integrated the electric field along that same distance, we would receive the voltage d on across that field, or the threshold voltage that would need to be achieved to let current pass through this diode. Now, why is this VDON important? Well, if we look back to our rectifier output, this rectifier output is for an ideal circuit, so it directly mimics this AC input. When in reality, it would have to reach a threshold voltage before these diodes were able to turn on. Now, because of this, the amplitude of a real rectifier output, including real diodes, would be somewhat smaller because you would take the Vin minus 2 VDON would be the peak of the rectifier output for a real rectifier. Now we can go and analyze the properties of the RC circuit. It's important to realize that for the RC circuit, it is a linear time invariant system. It's an LTI. Now, why is this important? Well, we know that LTIs operate under first-order differential equations that have no initial conditions. Now, the no initial conditions aspect is very important here because that means that at t equals 0, we start at a voltage of 0. Now, that can also be reflected if we analyze the circuit from an electromagnetics point of view, which would be when time is equal to 0, this capacitor will act as a short circuit, which means that all the current would flow through this short right here, and there would be no voltage drop along Vout, which means at time equals 0, you have a starting point of a 0 voltage. Now, as time goes to infinity, this capacitor in turn will act as an open circuit, which means you can equate the Vout to a voltage drop over the R2 resistor. Now, this voltage drop would then be R2 over R1 plus R2 times V would equal the Vout of this system. Now, why do we care about the Vouts of all of these systems? Well, that's because V is directly proportional to power. So power equals the voltage squared over the resistance or load in this case. So when voltage goes up, power goes up. So that's a really, really key thing to understand. Now, in this system, we know that it has an exponential increase, or a logarithmic increase until it reaches a cutoff point, at which point the diode switches and it's reversed. So imagine sort of a shark fin wave, where when the diode is reversed, it goes backwards. Now, in total, this power and this it sort of acts like this shark fin wave. When this exponential switch happens, it will originally follow here, and then it will exponentially decrease until it comes back up again and exponentially decreases. And that's how we can sort of measure the power of the system.